Let's evaluate the voltage gain, AV, of a common collector, this time using the T model for a transistor. Okay? All right, so let's convert this to the AC equivalent model using the T model for a transistor. And let's start from the right where the input is. Let's consider the capacitor a short. R1 and R2 are in parallel. Let's call that one RB. Okay? And we're going to call, let me write here, RB is R1 in parallel with R2. Okay. All right. So since we're using the T model, so what does that entail? The transistor itself, right here, this would be RE prime, plus the current source would be this way, which means this is the base, okay? This is the emitter, and this is the collector. So that's as far as the transistor T model looks like. Now, from an AC point of view, here's the collector, here's the base, here's the emitter. The collector is connected directly to VCC. In other words, in AC, this is directly connected to ground. Okay? And the base is to base, but the emitter right here is also connected to RE right here. Okay? And now what else? Well, our output from this point is measured right here, V out. Since V out is the voltage output over the load. Now you can put the load right here, and that would be our load right here. So V out would be the voltage against the load, and the load is between the emitter to the reference. So that would be the model. Now, if this was the pi model, remember, then it would look something like this. So let's do that quickly. So as a review, so this is the voltage source here. Hang on a second, let me do it again. So this is the voltage source, okay? Ground. We will still get RB, okay? And what we will get also is beta RE prime, okay? And then from that point, we can flip the current source down to ground, and it's pointing out this way, and then you would have RE right here and RL right here. That would be the pi model. That would be RE, RL, and this current source here is simply beta IB, or in other words, it's the current IC, right? The collector is going to be here. The base is going to be here. The emitter is going to be right here. Okay? And then the current going through beta RE is IB. And the current going through RE is IE here. So what do we have here? Here we also have IE. Notice everything is lowercase, right? Little IB is here. So be really careful that the current little IB does not go through the resistor here. It really is the sum of IC plus IB going through little RE, and it's almost the same current going through RE here. Except we have to be careful, we have a load here. Okay? If we have a load and V out happens to be here, then V out is here as well. So we can say safely, right, that the current going through RE right here times RE is V out. And that's going to be helpful in terms of determining what is basically the ratio of the output voltage versus the input voltage, which is this one right here. Vn is applied from ground to base here. All right, so that's Vn. All right, so what can we do? Well, if Vn is from here to here, then it is from here to here as well. That is Vn. right? So, and Vn will be a composite of these two voltages, this one plus this one, right? So that's basic Kirchhoff law. So what kind of current is going through little Re prime? And what kind of current is going through Re? Okay? So those are things we need to worry about when we're solving for AV. Let's go ahead and look at the current, right? Going through here, let's assume that IE here is the same if, let's say, we have an open circuit, right? So that means without load, this IE is the same as this one. So that's going to be significant. So without load, in other words, no RL, right? The same current is going to go through little RE and big RE. Okay? So how can we write this? So Vn is going to be equal to little IE times little RE prime plus little IE times RE. Well, what can we say about this? If you think about it, Vn is the sum of these two, right? So we can actually factor little IE, and that would be little RE prime plus big RE. How about V out? Well, V out itself is little IE times big RE, right? So that would be the voltage from here to here times the current going through RE. So V out over Vn with no load is going to be equal to big RE divided by RE prime plus RE. Now, this is very important. So this will be the exact formula with no load. But we know also that little RE prime is much, much less than typically RE. So this implies that AV, which is equal to V out over Vn, right, is approximately equal to RE over RE, which is approximately equal to 1. Okay, so we can approximately say it's almost 1. Usually the real value, since this has some value, AV is going to be in the order of 0.9 something, right? So typically this is where you're going to find yourself with the voltage gain. Okay, so having solved for that using this, so what's the next thing? Well, with load. Are things going to be different? Yeah, because the out with load, Vn, it's still going to be equal to IE. So let's put the load back here. IE times RE prime plus IE times, we're going to think about what's going on here. Here's a little IE. IE is here. It's going through the emitter. Let me just draw it a little bit bigger here. Here's RE prime. This is the emitter, right? But then you have RE here in parallel with RL. Little IE is right here. It's the current going through both branches. So we have a current here and a current here. So this little IE is RE in parallel with RL. Major difference here. So we have to consider the load. The load will have an effect. So we know this. How about V out? Well, V out is simply, again, and let me factor this out here. So this little IE, RE prime plus RE in parallel with RL, right? So slight difference between this and this. And then V out, it's still IE times RE in parallel with RL. Okay, well, what is that? Well, that means this implies that AV, which is equal to V out over Vn, is going to be equal to, and that would be IE times RE in parallel with RL divided by, and that would be IE times RE prime plus RE in parallel with RL. The IE components can disappear, so it's equal to RE in parallel with RL divided by little RE prime plus RE in parallel with RL. Now it's a matter of scale. RE prime will still be much less than RE in parallel with RL. In other words, we can approximate AV as approximately equal to RE in parallel with RL over RE in parallel with RL, which approximately leads us to 1. So same story. And we're going to be in the order of 0.9, since really that little component there would shift the denominator to be a little higher than the numerator, so it's not exactly 1. So I hope this was instructive in terms of figuring out the voltage gain, or AV, using a T model for a common collector.